This is example 4.4, a problem in which we're going to find the formula of a simple hydrocarbon, CxHy, by combustion analysis. Watch the video and then we'll solve the problem.
A combustion reaction of a compound with oxygen forms water and carbon dioxide. The water, represented as blue speckles, is trapped in one chamber, and the carbon dioxide, represented by white speckles, is trapped in a separate chamber. The mass gain of each chamber can be used to calculate the empirical formula of the compound.
This is the strategy map for example 4.4. In this problem, what we would like to do are determine the empirical and molecular formulas for CxHy, a simple hydrocarbon. And we do that by burning it and collecting the CO2 and water, as you saw in the video. And so we know the masses of CO2 and water, and we also know the molar mass of this compound, which we determined in a separate experiment. What we're going to do in the first step is calculate the amounts of CO2 and water that came out of that combustion reaction. That is to calculate the numbers of moles of each thing. And then in the next step, we'll relate the number of moles of CO2 to the amount of carbon that was back in the original compound, relate the moles of water that came out to the number of moles of hydrogen that were back in the original compound. And then we'll take the ratio of the number of moles of carbon to the number of moles of hydrogen. How many hydrogens are there per carbon atom? How many moles of hydrogen are there per mole of carbon atoms? That's the calculation of the empirical formula. And then from that and the molar mass, we can determine the molecular formula. Okay, now let's work out the problem. When you burn this hydrocarbon, CxHy, you're going to get some CO2 and some water. Some amount of CO2 and some amount of water. And the important point to realize is that every carbon that was in this original compound is now in the CO2. So if we know the number of moles of CO2 produced, we know the number of moles of carbon that were in that compound. Furthermore, all of the hydrogen that was in that compound now shows up as water. But the important point here is that there's 2 hydrogens captured in every molecule of water. So we have to take that into account in figuring out how many hydrogens were in the original compound. So let's work out the numbers. Well, you knew in your experiment that you found 3.447 grams of CO2. You know its molar mass, 44.01. So the number of moles of CO2 is 0.07832 moles of carbon dioxide. Now remember that all of those carbon dioxides carried away a carbon from the original compound. So we're getting close to the information we need. Now let's look at the water. We captured 1.647 grams of water. We know its molar mass. And so we calculate the number of moles of water, 0.09142 moles of water that were collected in our compound. And here's the important point again. All of the hydrogens that were in the original compound are now in this water that we captured in the experiment. Okay, now we can begin to work out the empirical formula. Okay, now we know the combustion of our original compound led us to 0.07832 moles of CO2 and 0.01942 moles of water. How is that related to the amount of carbon that's in the compound and the amount of hydrogen that's there? Let's look at the numbers. 0.07832 moles of CO2 came out, and we know that for every mole of CO2 that came out, there must have been 1 mole of carbon back in that original compound. So we know how many moles of carbon there were in our sample. What about hydrogen? That goes to the water. 0.09142 moles of water, and that's related to the amount of hydrogen by this factor. We know that every mole of water that comes out, there must have been 2 moles of hydrogen back in the compound. Every molecule of water that comes out in the combustion reaction means that there were 2 atoms of hydrogen back in the compound. So that means in this case, there must have been 0.1828 moles of hydrogen in the original sample. That's the information we need to solve for the empirical formula. What we're going to do is take the ratio of the amount of hydrogen divided by the amount of carbon. That tells us the number of moles of hydrogen per mole of carbon in the compound, or the number of atoms of hydrogen per atom of carbon in the compound. And here's an important problem-solving tip. we always divide the larger number by the smaller one. You can do it the other way, but dividing the larger by the smaller will give you a much more unambiguous answer. In this case, this ratio turns out to be 2 1/3, which means that there are 7 hydrogens for every 3 carbons. That's the empirical formula of the compound. We now know it's C3H7. We're almost there. We only need one more step to solve for the molecular formula. Our problem is nearly solved. We figured out from the experimental data that the empirical formula was C3H7, 3 carbons, 7 hydrogens in a formula unit. We also know that from another experiment that the molar mass of the actual compound is 86.2 grams per mole. Well, how do we translate that into a molecular formula? We know the molar mass for the empirical formula. If the compound was C3H7, we can figure out that it should be 43.1 grams per mole. If that were the actual formula, it would have a molar mass of 43.1. Well, how is that related to the actual molar mass? It's clearly half. The actual molar mass is double the empirical formula mass. Therefore, the molecular formula is double the empirical formula, or C6H14. So our problem solved. From the combustion analysis, we found that the amount of CO2 and water that came out told us the empirical formula was 3 carbons, 7 hydrogens. We knew from the experimental molar mass that the molar mass was actually twice that of the empirical formula mass, or a molecular formula of C6H14.